Okay, so for example 5.2, we have quite a few things going on. We actually have two different parts of this system that are working together. One thing is called the conveyor, so let me highlight that, and the other thing is called the bearing. Right? So the conveyor is going to index 8 inches in 0.4 seconds, such as just means it's going to move, while a bearing is pressed into a housing on the conveyor. Right, so when we take a look at that aspect, we also have to think about the bearing, which is going to travel 4 inches to meet the housing, then be pressed 2 inches into the housing, right? And then the entire press stroke of the bearing is going to take 0.6 seconds and return 0.4 seconds while the conveyor is indexing, right? So the indexing aspect of the 8 inches in 0.4 seconds is going to happen in that 0.4 seconds that the bearing is returning, right? So if we go right to all these things that are being asked, so this is a very good problem to review. We have a time ratio, which is just going to be the advanced stroke divided by the return stroke. Right, now that would be the press mechanism, as it says right here, the press. So that would be 0.6, which is the advancing. And then we have the 0.4, which is the return. And we get another 1.5. Right, it says to find the cycle time. That's pretty easy. That's just going to be your delta t cycles is a summation of 0.6 plus 0.4, which is going to equal 1 second per revolution. All right, so I think we can see it's pretty easy. If it's 1 second per revolution, then we can go to, if it's asking for a motor speed, that's the omega. So in omega, we just go ahead and flip over the cycle time, which is pretty easy because it's a 1. So 1 divided by 1 second per revolution, which is equal to 1 revolution per second. Then you can multiply that by 60 seconds over 1 minute. And this is going to equal 60 RPM, 60 revolutions per minute. Alright, so we got the time ratio, the cycle time, and the motor speed, 60 RPM for that first part. Alright, the next part is to sketch synchronized timing charts. So we'll go ahead and go to another slide to free up some space for us. All right. So the charts are going to start with first figuring out the peak velocities. Acceleration is also going to be useful, but let's go ahead and find a velocity. So for the let's start with the conveyor. All right. So for the conveyor, we know that it moves 8 inches. And here's the velocity, peak velocity equation with the delta R. All right, so 8 inches is equal to 1/2. Here's the peak velocity times the amount of time that it took to travel that 8 inches, which is 0.4. This is for the conveyor. All right, so we'll get a V peak of 40 when you solve that, inch per second. All right, we'll do the same thing to find acceleration, which is the delta R is equal to 1/4 acceleration, 0.4 squared. So we see a lot of them using the 8 and 0.4, but we have the delta t squared and we have the 1/4 in there, so we're going to be careful about that. All right, so your acceleration that you solve for is going to be 200 inch per second squared. All right. So for the conveyor, we can go ahead and draw the timing chart for this pretty quickly, right? Because we could see 0.4, let's just say it comes out to this time right here. All right, and since we have a peak velocity, we could just go ahead and draw a triangle just very quickly. Right, and that's the only time that the conveyor is actually going to do something. It's going to index in that 0.4 seconds. All right, and we know that that peak is 40. Right, so on this side, we're talking about a velocity in inch per second, if I can label the axis there. And then we got time in seconds here on the x-axis. All right, so it reaches a maximum of 40 in at 0.4 seconds. All right, let's go to the bearing. So I'll put the bearing information over here. So the bearing, we know that there's a couple of parts to it, right? So during that 0.4 seconds, it moves 6 inches. All right, so that was the, if we go back, that is the return, right? Return 0.4, but it says that's why the conveyor is indexing. And we know the bearing has to go 4 plus the 2 overall distance, so that's where the 6 inches comes from. So we got 6 inches is equal to 1/2 peak velocity times 0.4, and we have the peak velocity equaling a -30, and kind of skipped over that negative part, right? But this is because of the return aspect. So the delta R is actually a -6. So that's where we get a -30 inch per second. All right, and then we can go to acceleration. So we have a -6 is equal to 1/4. Right? Acceleration times 0.4 squared. All right. And when we solve for acceleration here, we should get we will get a negative 180. That'd be inch per second squared. We're not actually going to make a timing chart for acceleration here. You'll see that in another example. But it is useful to get that acceleration out of the way. All right, so this is for the return. And then we can go to the advance stroke. So the advance stroke uses the same distance, positive because it's going to advance, is equal to 1/2 peak velocity during this section. It takes a little bit longer, 0.6 seconds. Right? So your peak velocity is going to equal 20 inch per second. And then do the same thing for acceleration, 1/4 acceleration, 0.6 squared. So your acceleration in this section is going to be 66.67 inch per second squared. So something I just noticed here, we've got to change this to a -150. If you actually solve that, you will get a -150, not a -180. All right, so now we're ready to graph the second part of this. Right now we really do see two sections, 0.4. The overall cycle takes 1 second overall, so we'll just say here's 1 second. It's not exactly to scale. All right, but we do see that the return aspect had a -30 for the first part, so that's where we will go a little bit deeper here. And so -30 is down here. We know this is inch per second. This is second here for time. All right, so we got that down to a -30, and then the other velocity is a +20. So we'll mark off +20 right here, and that's where the next section comes into play. So, so that's how you would draw your timing charts. Let's go back to the question here. It says estimate the peak velocity and acceleration of the housing on the conveyor. It's pretty easy. We already determined all these things. Peak velocity and acceleration of the bearing, of the housing, of the this is bearing press movement, and then we have bearing press return. All right, so the conveyor, and then the advancing, and then the return. We did all that already right here. Okay, so if we can think about the conveyor, right? We found the 40 and the 200. For the advancing, which is that second part of the question, we have the 20 and the 66.67, and the return is a -30 and a -150. All right, and the last thing is something that I like to do is called optimization, and that's the motion. So we're optimizing the motion so the maximum acceleration of any part is less than 1 g, which is 386.4 inch per second squared. All right, so how do we get that done? Well, it all starts with finding the biggest magnitude of acceleration that we have here, which is right here, 200 inch per second squared. So if we change that particular acceleration to 386.4 inch per second squared, right, and then use the acceleration equation, right, which was delta r is equal to 1/4 acceleration times delta t squared, and we want to solve for that delta t. So delta t is equal to the square root of 4 delta r divided by the acceleration. All right, and so we have to go back to what is the delta r for that 200 inch per second. That delta r was an 8. Now we go back here, right, we plug in. So 4 times 8 divided by 386.4, because that's what we're now assuming we are trying to optimize things, so we change that 200 into 386.4. And we get around a 0.288 seconds, because this is a delta t. All right, so that's, if you remember, was for the conveyor, right? And that conveyor takes place in the 0.4 seconds, so that would be the return stroke. All right, and so if we remember, Q is equal to the advancing, right? And we're going to call the advancing, in this case, we'll actually just call it the second here. All right, and then we have a 1. So it's really how you're ever going to label this, but it might be even easier just to say this is the advance and this is the return. Right. So the Q is not going to change. So that's a 1.5 is equal to the advance, right, which is the sorry, is what we're trying to find. So let me make sure we get that right. Delta t advance, because we know that this time right there was related back to the return of the bearing. So we got a 0.288 for the return. So if I solve for the delta t advance in this basic algebraic expression here, we get a 0.432 for the advancing time. All right, let me just check that real quick. 288. All right, 1.5. All right, so we have the 2 times for the advancing, for the return. If I want to use that or use that to our advantage, we know that that's a delta t of the cycle is equal to 0.432 plus 0.288. All right, we get a 0.72. Then we can go right to the omega. All right, the omega is equal to 0.72, but flipped over. Right? Remember, this would be the amount of seconds in 1 revolution. So this would be 0.72 revolutions in 1 second. And then we can convert that to RPMs by just multiplying by 60 seconds over 1 minute. And when we do that, we get an 83.3 RPM. All right, so this is, if we speed up the system to 83.3 RPM, then we're getting the maximum output, because we know what the maximum acceleration that we could actually put into the system. We're never going to go over that for any part of this system. Okay, so for the quick return mechanism example here, we have we're trying to design it so that we have an outward stroke of T1, return stroke of T2. right? We want to determine the time ratio, imbalance angle, and speed at which the mechanism should be driven. So this is very similar to an example that we did in the lecture, so should not be very difficult. So let's go ahead and label these guys. We already have the T1 and T2 ready to go. And we'll go ahead and get the Q. Right? So our Q value is going to equal T1 divided by T2. Right, T1 is our outward stroke, right? Our advancing and return stroke is T2. Right? And you can, if you want to label it as return and advancing, that's probably easiest. Advancing will always be on the top, right? And the longer longer amount of time is going to be on the top. So that's another way to think about it as well. So 1.1 divided by 0.8 is going to be a 1.375. This way to go. So we have beta is what we're going to try to find now. So 180 degrees times the Q minus 1, 1.375 minus 1 divided by 1.375 plus 1 is equal to a 28.4 degrees. And then we'll go to the omega, alright, which is just 1 revolution divided by the time. And so this is another way to get it done. You can add up the times, call that seconds, right? So it takes 1.9 seconds to do 1 revolution. And we've already flipped it over because it's the omega. So it's another way to think about it. So the cycle time is a 1.1 plus 0.8, which is 1.9, and that would be, that's a second over revolution. So we're just inverting it for this omega. And you're going to go ahead and multiply it by 60 seconds divided by 1 minute to get you RPM, which is going to be 31.6 RPM. Alright, so that's not too bad. Let's go to another one, right, where we have a quick return mechanism. Drives at a certain omega. Omega is 180 RPM for this example. Has an imbalance angle of beta. Want to determine the time ratio and the time to complete the outward and return strokes. Alright, so we can go ahead and get that omega is equal to 180 RPM. Alright, and actually let's put it to this format, revolutions per minute. If I get that into how many seconds per revolution, alright, so what does that mean? That means that we have 60 seconds in every 1 minute. Alright, and so we can say that's equal to, minutes cancel out, so that's equal to 3 revolutions in 1 second. I don't need to put the 1, let's just put in the seconds. So that's 180 divided by 60. Alright, so if we inverse this, so delta t of the cycle is equal to the 1 over omega, but it's in terms of if your delta t per cycle is going to be in basically just flipping over the omega, right? So flip that over, we know it's going to be 0.333 seconds per revolution. So let's go ahead and find Q. Q is equal to 180 plus 25, which is your imbalance angle, over 180 minus 25, which is equal to 1.322. Right, and don't forget your delta t is just the summation of the T1 and T2, so T1 plus T2. And then Q is equal to the advanced stroke, which is T1 divided by your return stroke, which is T2. And then from what we have here, T2 is equal to 0.333 minus T1. So then you can plug this into the denominator over here. We have T1 divided by 0.333 minus T1. Right, so with the 1.322 and the T1 over 0.333 minus T1, you could solve for T1, and T1 turns out to be 0.188 seconds. And you could just plug it right into here and solve for T2, which is equal to 0.142 seconds. Let me do the algebra. Alright, next up we'll do some timing charts. And let's go ahead and get started for that. So we have a punch press. There's only one thing to worry about here. It's a punch press moving downwards a certain amount of distance, 1.5 in 0.6 seconds. Returns in 0.35 seconds. Determine the time ratio and crank speed. And then it wants us to sketch the timing chart and estimate the peak velocity and acceleration of the motion. Alright, so we'll start with finding Q. Q is equal to 0.6 divided by 0.35, which is a 1.714. Talking about the 0.6 seconds to advance, return in 0.35 seconds. All right, we'll go to omega, which is 1 revolution divided by the summation of those two times, so it's going to be 0.95, 0.6 plus the 0.35. And we'll also then multiply by 60 seconds over a minute. Don't forget this is seconds right here. Right? So seconds will cancel out, and then we get a 63.2 RPM for the crank speed. Alright, peak velocity is going to be related back to our equation, right? So we have delta R is equal to 1/2 peak velocity times delta T. Alright, so we'll just plug in. You have a distance travel of 1.5, as we know, and then it takes a certain amount of time, so just depends upon which way we want to think about this. All right, so we can do the advancing aspect. Right, so that would be the 0.6. Okay, so that means V peak is equal to 2 times 1.5 divided by 0.6. We get a 5 inch per second for the advancing peak velocity. Alright, so we'll put 5 there. Alright, we could do acceleration while we're at it. Okay, so delta R is equal to 1/4 acceleration delta T squared. Alright, this is 1.5 here. This is 0.6 squared here. And when we solve this for acceleration, we get 16.67 inch per second squared. Let's keep on going. That was for the advance. I want to make sure you're keeping everything situated here. That's for the advance. It takes 0.6 seconds to do that. We'll do the return, which happens in 0.35 seconds. Alright, so we can do that very quickly here and say that our 1.5 distance is equal to 1/2 times your peak velocity, and that's going to happen in your 0.35 seconds. So your peak velocity is equal to 8.57 inch per second. And then we can go to your acceleration. 1.5 is equal to 1/4. Acceleration 0.35 squared. So your acceleration is equal to 49 inch per second squared. Alright, so now it's time to graph this stuff. Alright, so it says, sketch a timing chart and estimate the peak velocity and acceleration of motion. So, even though this is not required, I'm going to draw another chart, which is just a displacement, right? Because we notice that displacement is going to happen over a certain amount of time, which is at 0.95 seconds. It displaces 1.5, all right, that would be in inches. All right, so it's going to essentially be something like this, right? Because we know the velocity is going to be positive, and then, well, I should say it's going to increase. The velocity is going to increase to a certain peak, and then it's going to decrease back to 0. All right, so hopefully this gives us an idea. This is your displacement graph, where we can see like we displace to 1.5 and then we come back. But we don't do it in a triangle format because we got to ease into it. So now when we draw the velocity graph, we already know the values, right? This is going to happen in 0.95 seconds. We know that 0.6 is an important time for us. So the peak velocity in that 0.6 for the advance, right, was 5. So we draw a triangle for that. Then the return had a 8.57. Okay, and really I should have put a negative sign here to get the negatives of these guys. All right. So we have it a little bit steeper. Right? And there'll be a negative 8.57 on the graph, and we would have positive 5 right here. Okay. And this would be inch per second for the units, and obviously this would be seconds for the units there. All right, and then we can do one more graph, which is the acceleration. All right, and that would be 0.95 here. We can say 0.6 here, and we could just kind of take a cue from our triangles, right? We know that this part of the velocity, that's a positive acceleration, so we actually know that that is an acceleration of 16.67. So it's going to be 16.67 up to the halfway point, and then it drops to a negative 16.67 because that's this part of the triangle. All right, and then we continue to be negative for 49, so that goes pretty low, right, up to a halfway point, and then we go to a positive 49. So if I label all the axes here, we got 49 here, we would have a 16.67 here, negative 16.67 here, and a negative 49 here. These would be inch per second squared, and we would talk about seconds on this axis. All right, so take a look at the important one would be the velocity graph, and then also the acceleration graph. So that you got to make sure that you know how to graph that. All right, last couple ones here, go pretty quick. So for the designing of a slider crank mechanism, all right, with the time ratio of Q, we're going to use the slider crank. We actually have two different examples here. So for the first one, which is actually just an inline slider crank, we'll go pretty quickly through that. Right, Q is equal to 1, and your delta R for max is 2 inches. Your time is 1.2. That's the time per cycle. All right, so since Q is equal to 1, that means it's inline. Makes things very easy. That means an L2, and all that we're trying to figure out is what's L2, what's L3, and what's L1, if any. If it's an inline, there is no L1, so keep that in mind. Alright, so L2 from the equation is equal to delta R4 max divided by 2. Right? So that would be 1 inch. That's easy. So L2 is 1 inch. Now L3 really could be anything that you want as long as L3 is bigger than 4L2. So since L2 is 1, let's just say 5L2, that would make L3 to be 5 inches. All right, and it also asks for the crank speed. Right, so omega is equal to 1 revolution divided by the time it's taking to complete this, right, which is at 1.2 seconds. And if you go ahead and convert this just by multiplying by 60 seconds in 1 minute, then we can get 50 RPM. Alright, so there's your final answer there. Alright, so we can find L2, we find L3, even though it just fits a criteria, and we already know that L1 for the first part is 0. Now let's go to the second one, which is an offset, using this information here, which is right here. All right, and that means we're actually going to have to use the L1, L2, and L3 equations to get those answers there. So let's take that information with us. Q is equal to 1.2, delta R for max is 0.375, and the time per cycle is 0.25. I'm sorry, 0.025. All right, so take that into account. We can get a beta pretty quickly. 180 times 1.2 minus 1, because the Q is given to us, right, as 1.2. And then on the bottom we have 1.2 plus 1. This is going to equal 16.36 degrees. All right, so hopefully you can see what we need. We do have delta R4 already, which is 0.375. We just found the beta, so the only thing that we need is what is theta m. Now this is where it gets a little interesting. We actually assume that theta n is 10 degrees. So that means theta m is that 10 degrees plus whatever beta is. So that would be 26.36 degrees. Right, so this is an assumption that we make, and it's a reasonable assumption because that's where your minimum theta, which is theta n, should be 10 degrees or above. If it gets too small, then it's not good for the actual system. All right, so since we have beta, we can plug that in, and I'm just going to go ahead and do that for you guys. L1, L2, and L3, after you plug into each of them, are 0.1026, 0.1799 for L2, these are all in inches, and 0.4112 inches. So there is your L1, L2, and L3. Just go back to make sure we know what's being asked here. We have those distances, and let's go ahead and do a crank speed real quick. All right, so we know that time per cycle 0.025. So that means omega is 1 over, that's 1 revolution, over 0.025 seconds. We just multiply that by 60 on top, 1 minute on the bottom, 60, 60. So we have omega being 60 divided by 0.025. We have a 2400 RPM.